Well, first of all, thank you for having us and allowing us to join your education day. When I get into the presentation, you'll see that education, in my opinion, for this industry that we're in is really, really important. If you can go to the next, do we have a? Excellent. So a little bit about me. I've had about 25 years in the high volume automotive manufacturing. And that's a little bit different background than what you guys have had, but there's a place where it overlaps, and that's with this 3D printing and additive manufacturing. I saw how 3D printing and additive manufacturing could really have an impact on traditional manufacturing and our efficiencies and new ways to manufacture things or new ways to run processes. And I see how that applies even to your industry as well. And that's why I got into 3D printing and additive manufacturing. I do call myself an expert in additive manufacturing now. I've been teaching at Mohawk College, the same subject, and I helped them set up an additive manufacturing facility there, both in metals and plastics. But I know about, maybe this much of additive manufacturing, and there's this much to know. The difference is that the average person only knows this much today. That's how I can call myself an expert today. So my company today is called Canadian Additive Manufacturing Solutions. We are a solutions-based company trying to connect traditional industries with additive solutions. So meaning we're experts in additive. We're not experts in automotive manufacturing. We're not experts in jewelry design. We're not experts in the medical side. But what we find is that we pair up or partner with people who have expertise in those other fields, like yourselves. That's where we find the synergy and the opportunity to really take the technology forward. The time that it would take for me to learn what you guys know is impossible. And the time that it would take for you to learn what we know would be longer than just tomorrow. And so if we work together, that's how I think this technology can go forward. So we do sell, a little bit of disclosure here. We are representatives for 3D Systems, for some scanning products, and one of the products that we're going to talk about is D2P, die-come-to-print software. And the processes we're presenting are not all approved in all different countries. We have some approvals in the US and some of the software tools, but I'm going to talk a little bit about that as one of the barriers as we go through the presentation. Yeah, and certain materials have got biocompatibility that you'll see back here at the back. So this is kind of the agenda or the objectives for today. We met Carrie and Karen at the RSNA last year, and we wound up with an invitation to come and talk. And for me, I think there's about 1% of the population who really understands additive manufacturing and how to use it and really take advantage of it. And so what we find ourselves doing is not just selling products, but we really have to educate. We really have to spend time with people to help them understand how to use the technology before they're able to adapt it. And so this opportunity to talk and tell you a little bit about the technologies is perfect for me because we spend so much time educating. So I'm going to talk about 3D printing, the technologies today, and a little bit about a few of the key processes. So you get a little bit of background, a little bit of a primer. Then I'm going to talk through what I see as applications. And this is the place where we would need to collaborate together at some point to execute, but you'll see, I think, things that will resonate for you as opportunities. And then we have a second part to the presentation, which is over at the back here, where we're going to have a hands-on display. We have a whole series of 3D printed models from each of the different printing technologies to get you a sense of what's possible to be produced from creating physical models. But also what's possible from a virtual reality perspective to analyze and review the data that you're already collecting on a daily basis. And you'll get a chance to, if you want to, you'll have an opportunity to put the headset on and go through and explore some of the models that have been created, and I hope you'll have time to do that. So a little bit about the technology. So the first thing that I usually educate or talk about is that 3D printing is always, almost always, we'll say 99.some-odd%, a layer-by-layer manufacturing process where we're building up an object one layer at a time. and they're almost always horizontal layers. So it's the picture here of, the slices, that's almost the way everything in the back here has been produced. Another key takeaway is that this is taking digital data and making it into a physical object. What you guys do on a regular basis is you take physical objects and you turn it into digital data. Then what we're going to talk about is doing something with it and then making another physical object with it. So another distinction, and this is a little bit of my own opinion, 3D printing has been around for quite a while. They're printing of models, mock-ups. There's a figurine of my passed away puppy at the top there. There's mock-ups or prototypes, like a housing on the right-hand side here. And I usually call that 3D printing. Additive manufacturing, I use for the term where we're creating a final product, like a finished, usable item. Now, that's my definition, but at the end of the day, the news uses it almost interchangeably. So just know about the two words, but unfortunately, the news uses them so interchangeably that it's almost impossible to control that definition. But for my presentation, they'll be used. We'll talk about them interchangeably to some extent. If there's anything you take away from the discussion today, it's this slide here. And the whole reason that additive manufacturing or 3D printing is interesting to me and to many is because it allows some new design element or manufacturing element that couldn't be done before. And these are the 4 key points in my mind. The first one is a little more on the engineering side, but we can design things for their function. I grew up as an engineer. I was educated as an engineer. We were taught design for manufacturing, and we were taught to design things that could be made. We drill holes in a straight line, and they're round. If I say, hey, I want a triangular hole, and I want it to go like this, I'd get kicked out of school, because you'd be like, no, you can't make it, so why are you designing it, right? Well, today we can, and so now we can design for the function. And a little crazy idea on the far right there, and there's a sample at the back you'll see, is osseointegration structures on the surface, 3D printed in titanium. Well, we could never manufacture that before. You couldn't wire EDM that, you couldn't machine it, you couldn't injection mold it, you just couldn't do it. So this is a good example of design for function versus design for manufacturing. So similar point is the impossible geometries are possible. But the next one, which really hits us, is mass customization. So meaning we can produce products that are different for each piece. We have bottom center there, we had a project with a orthotic manufacturer, and we're taking scan data of a person's foot and making, there's just prescribed adjustments to be made. Those would be made in the 3D digital model, then we would 3D print the orthotic. But in the box of printing, every one of them could be different. Like meaning with the name of the person printed on the bottom of it so they don't get mixed up. And so that's called mass customization as opposed to injection molding one size fits all or a small, medium, and large, right? And so this is the other really big principle that 3D printing and additive manufacturing allows. And that's going to be a common theme through the presentation today because that lets us make patient-specific items. So no discussion about additive would be complete without a little bit of history. And I'll go back in time here to 1983. There's a fella named Chuck Hall. He invented a process called stereolithography. It's known today as SLA, and it's a very common process in additive manufacturing. And it remains essentially unchanged since 1983, using UV curable resins and a laser to cure them, layer by layer by layer. So you see a few other milestones on there, but the point here is, hey, wait a minute, this is not that new a technology. Like the news would have us think that, hey, there's something new every day, every day, every day. Well, there are new things, but they're really just spins on the existing technologies. There's a core set of technologies that I'll talk about next that really still prevail and are there for us to use. So the ASTM group, another standards group, has tried to help us here in defining names for all these different technologies. Because people will call it 3D printing and it's concrete. And then they'll say 3D printing and it's metal. And they'll say 3D printing and it's chocolate, like all these different things, and they all just get grouped together. Well, here's how we're defining the technical processes. Bottom right, you'll see the image there. That's the actual standard document. I'll have copies at the back if anybody's interested in it, but it's an important place to really kind of get your head around what technologies do what, right? What's for metal? What's going to give me strong parts? What's going to make me really accurate parts? So I'm going to talk really quickly about 4 of these technologies. This is called FDM, or material extrusion. This is the most common. I've got one on my desk at home. You'll see them in libraries. You'll see them in schools. And this is a kind of the starting point for anybody playing with 3D printing or additive manufacturing. It's perhaps the lowest cost, but perhaps the lowest surface quality and accuracy, but you kind of get what you pay for. Now, it does have the ability to be fairly large, but like fairly scalable, but it is the most prevalent. And there's we'll have samples at the back for you to see that. The next is called color jet printing or binder jetting, where we use a gypsum powder that's laid down layer by layer. You see a wiper that puts a layer of powder, and then a piezoelectric inkjet head, just like your inkjet printer at home, is instead of putting ink, it's putting a binder or a glue, only in the places for each layer that are necessary. And through that process, you build up layer by layer by layer of glued gypsum, and you wind up with a physical object. They added into it, put those inkjet cartridges back in with the color ink in them, and you make color parts, because the gypsum takes the color really well. So the parts are a little bit fragile at the end of that, but boy, they look real, like they are color and have some weight to them. And we've got samples again back at the back that I'd love for you to come and see and pick up and touch and see firsthand what they look like. The next is called material jetting. And this is using a UV curable acrylate. And what's interesting is we're also using the piezoelectric jets. So a lot of these technologies are based on our inkjet printers, like technology that actually isn't that new. In here, we're jetting, instead of ink, we're jetting a UV curable resin. So those little droplets on each layer are then cured by a UV light, you can see. So this forms really accurate parts. When you see the surface finish on these parts, it is the best in the class of all printers from this technology. The parts are UV cured acrylate, so they're a resin. They're not durable. You drop it on the ground, it may break, right, or chip. You're probably already familiar with UV curable acrylates and in the medical industry, and yeah, but it's very, very accurate. So the last one I'm going to talk about is kind of the holy grail piece, which is the powder bed fusion processes. And this is where we're laying, again, powder, but the powder this time is either plastic or metal. And it's then fused together each layer by a laser, which is actually melting the material instead of where we were gluing before or where we were jetting before. Now it's melting by laser, the powder bed layer by layer. So you can see on the right here, this is a 1/2 meter by 1/2 meter machine running titanium, and it's you see the recoating of layers of powder, and then you'll see the laser filling in where the part is layer by layer. So at the end of the day, this makes fully functional parts. When we make a cobalt chrome piece or we make a titanium piece, these have mechanical properties that are almost equivalent, if not better, in some cases, than traditional cast or wrought or machined parts. And you can see, of course, you have to excavate them out of the powder after, which that's what's starting to happen here. So you see a whole series of parts that are on a bed that'll be ready for use. And again, we'll have some metal powder samples at the back, so you just get a sense of what they are, and a few implant pieces that are printed also at the back, so you can see what they look like. So we're going to talk a little bit about the market. This is why I got into this, or part of why I got into this. Those graphs, I know you can't read the numbers, but the point of the slide is to say, look at the first blue and purple one. This is from the Wohlers report. It's the industry standard market data intelligence for additive manufacturing. But that curve is up to 2017, up to $7.5 billion industry for 3D printing and additive manufacturing. And those numbers don't necessarily mean anything to us, but what does is that shape. And that's a history chart. That's not a forecast. We have in manufacturing, we'd have a forecast. Oh yeah, we're going to sell all kinds of stuff, and okay, but no, this is what's actually happening in the world. This is a worldwide graph. So worldwide, that's what's happening. Well, we're a little behind here in Canada. We're a little slower to adopt. We're a little more cautious. But what it says to me is that's happening, and that means opportunity for business people, right? On the bottom is from the SME, Society of Manufacturing Engineers, and it's a little more medical focused, although it's the US, but it shows the US hospitals which are adopting the technology in-house. Well, it's got the same shape to it. And again, it's a history curve. It's not a, not a forecast. So that's interesting to me because it tells me it's happening, right? But this is a technology adoption curve. And just going to make sure I get the name right. Yeah, Jeffrey Moore, I don't really know Jeffrey, but doing some research on economics, he's got this theory that says, hey, the more disruptive a product is or a technology, there's these people who pick up on it early on, these visionaries that are like, yeah, this is great and it's going to be perfect. But there's always a lull in the actual adoption. And I think that's exactly where we are today here in Canada with additive manufacturing, where these technologies, since 1983 have existed, but why aren't we really using them yet? And there's lots of reasons people will come up with, but I think it's related to this. And if I overlay it with something else you might have heard of, which is called the Gardner Hype Curve, which is the other kind of concept of adoption of new technologies, I think this is exactly how it looks. And I think we're precisely in the chasm, and we're ready to move up the slope of enlightenment, which just is saying, hey, there's this point where people bought 3D printers in manufacturing. They bought all kinds of them. They bought them because, oh, I got to have it. It's the latest thing. It's the latest and greatest. But then they didn't know what they're going to do with it. So then it sits there. And then people say, well, I bought one. It's no good. I don't want it. Like, there's no point in it. But then what's happening today is people are thinking through the actual applications, what they're really going to do with it. And then they're like, I need that. And that's what's going to start to drive it out. And I think we're right in the bottom there. So a couple notes on why I think this technology applies here. This is my perspective. But we have an aging population. And I'm a manufacturing guy, so I'm going to talk a little bit like manufacturing. So we have an increased demand on our healthcare system. We have a capacity issue. And I think that these technologies can help us improve some of our performance, improve some of the capacity, again, to use manufacturing terms, to reduce the number of defects that occur, the number of returns that occur, which I think are all real terms in our healthcare system. And if we use these technologies, I think we can improve those metrics and therefore improve capacity, which I think is important for us as a society. So I'm going to have a couple case studies after this, but these are some of the things that I think are benefits. And that is that if we've got physical models, we might improve communication with a patient, their consent for what we're about to do with them. In the end, if we're able to make a better product for them or perform a surgery more accurately, maybe their comfort, maybe their satisfaction. If we can reduce the time to execute a surgical practice, because we have better guides, we have better tools, we have better practice or preparation, well, then that reduces the time in the OR, which improves the capacity of the whole system, which I think is an important piece. One of the things that keeps going through my head is if we have a really important, well, if I have a speech today, I practiced, right? I spent some time thinking through, try it through, read it again, do it again. If we have a basketball game, you practice. But a lot of surgeries, I'm not the expert, but I don't think you get to practice too well on the patient-specific conditions. You might have some textbook cases or you may have been trained, but there's the first time when you're going to do something you've never done, and you got to do it real time. Well, if we can have some models that allow you to do the practice, I think that's pretty cool. So, getting back a little bit more, a little less philosophical and a little bit more pragmatic here, if we talk about creating a 3D printed model, there's a workflow that has to go into this. And it starts with capturing the physical information and converting it to digital information, which is what we already do, you already do on a regular basis. But the next piece is software tools that are now available. And this is what we're going to have in our demonstration. Software tools that help us automate the segmentation process of that data to hone in on the piece or the product or the item or the component that we're interested in. From that, we create a 3D mesh model, which is the basis for most 3D printing processes. We can use our virtual reality systems now to better understand that item from the inside out. We can make the 3D print, and then we can plan and prepare for our surgery, which is that last part of now taking that digital back to the physical world. And of course, we might have an offshoot here if we think about designing patient-specific devices, like a patient-specific cutting guide. Well, we might take the 3D mesh model, take it into our favorite flavor of software for designing products, whether it be Freeform, whether it be SolidWorks or Siemens NX, whatever tool the device manufacturer is using. They can take that mesh data and custom design the items that we then can print. Again, it's back to that whole patient-specific mass customization opportunity. So that's a workflow. And the tools that are in this workflow all exist today commercially. Like the things that we do or the things that we offer, whether it be the printers for metal, whether it be printers for plastic or color, the software tools for segmentation, the software tools for designing the products, all of those exist in a commercial basis. Not even laboratory or university or research type basis. They exist on a commercial basis. They're all available to check the box, put the quote together, deliver the products, set them up, and use them tomorrow. Which is the part that gets to me is that, wait a minute, we can do this already. All the things that we're going to talk about in these next couple slides, we can do today. Yeah, there's some barriers, there may be some approvals, and there's understanding, but they're technically things we can do today. So this is my favorite slide. Kind of hits upon the key places that we might apply the technology. But I'm going to move on to the first one. So perhaps the most obvious or the most standout application is models for surgery planning or education to help teach or better understand. One of the case studies we have through 3D Systems, the doctor says, he said, well, I didn't think I ever needed it, didn't really see the use for it. But once he started to use it, he said, wait a minute, after I had physical models in my hand, there isn't a single practice that he did afterwards that he didn't change in some way. Maybe a small way, maybe a bigger way, but there's not a case that he didn't change his avenue or his path. Well, that's pretty significant to me. It means it's working. So yeah, between communicating, training, and planning, this is kind of, to me, the number one or first and easiest to adopt application. The approvals required to do this versus an implant is completely different, right? The next gets a little more complicated, and that is patient-specific devices, or could be implants, could be cutting guides. So there's a case study we have where you can see the jaw segmentation and a graft taken from another place on the body. Well, they used software tools to take the digital data that you guys created, converted it to models that they can design in their CAD software. They designed the cutting guides to take the graft, and they designed the cutting guides for the jaw, and those were used in the surgery so that they're a precise fit. Not close, but precise. And that's where we can improve the performance of the surgeries, right, if we're able to do this. And then, of course, I commented on it earlier, but when we get into this, it's almost a subject on its own, but the potential for osseointegration structures. Again, I'm not a medical practitioner, I'm an engineer, but I understand the mechanics of connecting things together, and that makes me smile, like there's something here. And we can do that, printing that. We have software tools that design the osseointegration structures that match those that have already been studied and determined to be the best geometries, and we have software tools that will create that. We have printers that can create that. Those exist on a commercial basis. On the treatment side, now that we can make patient-specific things, again, as an engineer, it's fascinating to me how we can introduce an object in front of a treatment radiation and cause focusing, cause diffusion, cause attenuation and change the way the treatment's delivered. Well, I can imagine now with these patient-specific devices that we can print from data from the actual patient, that we can improve the performance of this treatment activities. The last application I'm going to talk about today is a little bit of a diversion, but I think it's important to think about, and that is that when we make medical devices, like machines or electronics or treatment handling devices, well, somebody has to design those and prototype them, and they're low volume. It's not like when we make a car, we can make all kinds of pieces, try them all out, and make 1,000 trials. Well, with some of these devices, you're only going to make 1,000 pieces, so you can't really invest as much money. So what I find on the prototyping side is if we give an engineer an opportunity to design a product and say, be creative, he'll say, wait a minute, we're going to make an injection molding tool that's going to cost $200,000 or say $50,000, and it's got to work right away. So I can't take any risks. Well, if he could have a 3D printer that would allow him to print the housing, print the prototype, try something a little different, maybe make it a little bit, be a little crazy to think through the ideas, but he can print it, validate it's going to work before ever cutting the expensive tooling or permanent tooling. Or perhaps we 3D print the final component, and that's it. Meaning we only print, you're going to need 25 of these very custom devices. There's a company called ChipCare that I'm working with, and they're making custom devices that are going to be in foreign countries in the back country to do some blood testing, and we're able to print their products for them, so they're able to develop their product faster, and perhaps even some of the 3D printing will wind up in the final pieces. So it's not exactly radiology, but it certainly could be applied to the tools you guys use or touch on a regular basis. So I'm sure there's others, and we can have a good chat afterwards about what the challenges are about using the technology. Part of me says, hey, wait a minute, this all exists today in a commercial basis, as I said, but why aren't we using it? The first one I wrote is printing hardware, because people always bring it up. But in my opinion, there's a lot of different technologies, there's a lot of new things coming out, but there's an underlying core of technologies we're not really using yet, which we could be. So even if we just take the metal printing, or we take just the plastic printing, there's a lot of things we could already be doing. And I think the following are some of the other barriers. The software has just been changing. Like in the last few years, software tools to allow us to create these models more easily, not in just a research environment. That's a little bit of a game changer because that allows us to get those models really easily. And if we can make those 3D models that we might either just produce or use for further design work, if we can make them quickly, it can become routine. So to me, that's changing. Next is qualified people. Well, back to the education point. And the more I can help people understand, and then they can do their own research, we can collaborate, that to me is how we're going to remove that barrier. But the next one's change, because we're all humans, and disruptive change is like, well, why do I need it? I don't need it. I think this is another piece we need to think about. And I have a complete diversion on the side here. I say, think about plastics. So when plastics came out, we used to have metal chairs, right? And somebody said, oh, let's make things out of plastic. Let's make car parts out of plastic. It'll never work. It'll never work. Can't ever do it. And they'll be weaker. You won't be able to make, different designs. Who needs different designs? We got perfectly good designs. Well, there isn't a place you're going to go without touching plastics today, right? And I think that's the same with additive. It's not going to replace everything else, but it is going to change things. So it's more about us as humans being ready to try it, right? And regulatory requirements, of course, we have that in our industry. But I think there's a bit of a chicken and egg subject here, because if we're not really trying to use it and saying, hey, I need that, then there's no demand for regulations to change. So they kind of got to go hand in hand, but I think there's a piece of it where we got to start to try. So that's kind of how I'm going to leave it, is to say the technology's today, it exists. And I challenge you to think about cases. Partner with somebody, it doesn't have to be us, but somebody who knows the technology, and experiment with the virtual reality, experiment with the 3D printing, get some samples. And if you don't try it, you're not going to know. So And there are people like us who have some expertise in it, and we're happy to help you to figure it out and navigate through. So I challenge you to think about that. And really, that's my slides, other than to say, hey, come back and talk to us. We're going to have these samples, and there's my contact information. You're free to contact us. We have business cards. We'd love to help you learn more about it. So that's it. Thank you for your time.